So now we're ready to state the main theorem. It's called the common growth extension theorem. So essentially what it does, as I explained in the last video, is that suppose we are given some of these joint distributions, these mu of t1 up to tk. So here t1 to tk, they're all distinct timestamps. Suppose they satisfy the two property we saw from last video, so we call them consistent. Then you can construct some stochastic process so that their joint distribution is given by this mu. So there's a unique probability measure, mu on this measurable space, where this omega and b is essentially just either you can think about it as all the function from the r greater than or equal to 0 to r, and you equip with the Brown measure on each one of them, or you just take the product measure. Right, and this mu will satisfy this nice property. Basically, if you project it onto any of these timestamp, if you fix t1 to tk, then the measure of this mu, if everything else is just r, then you have that's just equals to mu like that. Okay, that's given by this probability measure you pre-specified before you construct this mu. Okay, so that's the Kolmogorov theorem. I'm not going to give a proof of this theorem because the proof is rather technical. There are two ways of proving this. If you follow Folland is using one way to prove is you construct certain dual space on the you construct a linear functional on the continuous function on the set omega, and then you use a result we didn't prove in this course. Basically, the dual space of the continuous function is given by all the measure with some nice property. It requires a little bit of topology, so I'm not going to do that. Another rough idea that's probably more natural, but they require some more technical detail, is that you do the Cauchy-Theodori. Okay, so basically, if you let this condition to be the star, then you use star to define some function mu, but you only define it on those boxes. Okay, so or it's this no longer called boxes because you have a bunch of infinitely many copies of these R, so they're called the cylinder sets. So you define the mu on these cylinder sets. Okay, so basically you fix a bunch of timestamp, finitely many of them, and you let the rest of them be the entire real. Okay, so t not equal to ti, and once you do that, you can extend it to the algebra of that. Okay, so now you have a mu defined an algebra of these cylinders, and then the natural step is to show that mu is actually a pre-measure. Okay, so that's how we construct measure on a more general space. You define something on an algebra, you show it's a pre-measure, and then you use Cauchy-Theodori to extend it. Okay, so Cauchy-Theodori to extend this pre-measure to a measure. Okay, so the proof of showing it's a pre-measure require a bunch of estimation. The those consistent conditions basically ensures that your mu is well defined. Okay, it doesn't matter when you have an algebra, the cylinder sets, you can represent them using different timestamp. You can write it as a union of a bunch of other things. The two consistent conditions make sure that your mu is a well-defined pre-measure, and then you use Cauchy-Theodori, and that's basically the mu you have. Okay, this mu will have some really nice property. I'm not going to talk about what they are, but this is essentially this common growth extension theorem. I want to briefly talk about the consequence of this theorem and why it's an important theorem in mathematical finance, especially in defining the Brownian motion. Okay, so let me talk about Brownian motion. So the definition of a Brownian motion, or sometimes called the Wiener process, is basically, if you heard a story, it's basically Brown, he look at all these small particles like pollen, and then it finds that they move in a certain random way. Okay, so that's where it's originated from. So now it's called a Brownian motion, or sometimes called a Wiener process. So it's essentially the following. So it's a stochastic process. So here I required it to be b of t. So here t is greater than or equal to 0. It's a continuous process. So every timestamp you have some b of t, a random variable. And it satisfies a few things. So first of all, let's just assume that b of 0 is always equal to 0. So it starts at point 0. And then because it mimics some random motion of some particles, so you would expect to be continuous. Okay, so this b of t, so you map t to this b of t is continuous, well, almost surely or almost everywhere based on your some whatever probability you have. And thirdly, the movement needs to be independent. So basically, if you have, say, t1 less than t2 less than tk, then the incremental movement, they're going to be independent. Okay, so if you consider this increments, this b of t2 minus b of t1, that's a random variable, and you do the b of t3 minus b of t2, and so on. So the last one is b of tk minus b of t k minus 1. So now you have a bunch of random variables. Okay, so the point is after, so basically the idea is the movement between the timestamp t1 to t2 will not affect how it moves between t2 and t3 and so on. So they should be all linearly independent, or not linearly, but independent as a random variable. Okay, so they're independent random variables. And finally, Brownian motion requires things to, is a limit of some discrete measure, and in statistical probability is basically given by this normal distribution. So it requires the bt minus bs. If you have two timestamp, then it will follow a normal distribution with mean 0, and standard deviation only depends on how long it lasts. Okay, so only depends on the time difference between t and s. So here t is greater than s, greater than or equal to 0. Okay, so basically it says if you start at a timestamp s, then the random variable at bt is basically follow a normal distribution, and the longer it lapses from the timestamp s, the more variance you get. Okay, so this t and s are any two elements, well, any two timestamp. Okay, so the idea is, well, now I have, if some stochastic process satisfy these four conditions, then we say it's a Brownian motion. But the first question you may ask is, does Brownian motion even exist? Okay, like I'm just imagining there's some nice properties, and I have no idea whether they exist. And this is how I use the common growth theorem to show that such a Brownian motion actually exists. Okay, so the idea is now you specify what these random variables should act. Okay, you have their joint distribution. So you have these independence conditions. So 3 and 4 basically specifies their joint distribution. And then we can use the common growth theorem is as long as they define some consistent measures, then you can put a random stochastic process so that it satisfies these joint distribution. So that's how you use it. Okay, so the theorem, I'm also not going to prove it, but the one big theorem is the Brownian motion actually exists. Okay, so Brownian motion actually exists. Okay, so the idea is essentially just apply the common growth theorem. So let me just briefly write it. So because you have for every time, so let's say t1 less than t2 up to tk, so you know these random variables by the Brownian motion, these b of t2 minus b of t1, and up to b of tk minus b of tk minus 1, it just follows independent normal distribution. And if you study some probability, you probably know how to convert their independent normal distribution into a joint distribution. Okay, so we get a joint distribution. or joint distribution measure, I should say, the mu of T1 up to Tk. That's basically what we think it should be, okay? And because for these timestamp, if I pick T1 less than T2, I pick the timestamp in the increasing sequence, then I can just fix it as my mu of T1 to Tk. If I swap the order, then I use the same mu. Basically, I can just always assume the timestamp is increasing. Okay, so the first consistency condition is trivially satisfied. And you can also check the second one is also satisfied. Okay, it really follows from these joint normal distribution. There's not much to see here. Okay, but anyways, you can verify these mu of T1 up to Tk, these families, they're consistent. Okay, so they're consistent. So because they're consistent, then by the common growth theorem, so the extension theorem, I can get these random variables Bt, a stochastic process that satisfies these joint distributions. Okay, so I got a Bt like that. All right, so let's go back to the conditions. Well, I can just pretend B0 is equal to 0, so that's simple. Okay, the joint distribution, because I specified they have to be the joint distribution given by these normal, so the 3 and 4 are also trivially satisfied. But there is one little problem. I need to show that this Brownian motion needs to be continuous. Okay, so that's slightly more difficult. And to show it's continuous, there are two ways to do that. If you follow Follon's textbook, okay, so I'll briefly explain how to do that. Basically, you try to show that this measure mu only concentrate on those continuous trajectories. Okay, so the mu, the common growth extension, you get a measure mu. You want to show that measure mu, when you evaluate on those continuous paths, that measure is going to be 1. Okay, so it's going to be concentrated on continuous ones. So from there, you know, wow, this B of t is continuous almost surely or almost everywhere. And one other way is probably a more standard way is to show that you first use the common growth theorem to extend it on all the rationals, and then you try to go from rationals to real. Okay, so you try to show once you define on rationals, then things are continuous enough so that you can extend it to real. Okay, either way works, but let me just briefly explain Follon's idea. Okay, so to show this continuity. So I basically want to show that let's consider the set where all these trajectory is actually continuous. And so let's take omega from these omega. Okay, so remember this omega is essentially a map from r greater than or equal to 0 to r, a real value function basically give you each time you return a real value. Okay, so that's my sample space. And when is it continuous? Well, so this omega is continuous. Let's recall some basic calculus. Well, if it's continuous, well, it means omega, if I restrict it to any finite intervals, that's going to be continuous. Okay, so for every n inside n. Okay, and well, when a function is continuous on a complex set from 0 to n, then it's actually uniform continuous. So this is first year calculus tells you this is also uniform continuous for every n inside n. Okay. Well, uniform continuity, just let's write out the definition. Basically, I say for every epsilon greater than 0, I can find a delta which basically works for everything inside my interval. Okay, so that for every x and y inside 0, and then I have omega of x minus the omega of y going to be less than epsilon if I have these x and y are x minus y is less than delta. Okay, so as long as x and y are close enough by this delta, then I have these the w function, the omega function, their value is within epsilon. Okay, so I can, well, here epsilon and delta, they're just basically some real. So I want to make them some countable union. So I can write them as a union and intersection, countable union and intersections of a bunch of sets. So that's what I'm going to do. So basically it means for every, let's say 1 over j greater than 0, there exists a delta so that, well, delta has to be greater than 0. So there exists a, say 1 over k. So here's 1 over k greater than 0, so that for every x and y inside these 0 n interval, and if I have x minus y is less than 1 over k, then I must have the omega x minus omega y is less than 1 over j, okay? So why do I want to write it like that? Well, it's essentially, I can now translate all of these as a bunch of union and intersection of stuff, okay? So basically, so here omega inside this big omega, where omega is continuous, is essentially just given by all the omega that satisfy these conditions. So basically, I need for every n in n, so whenever you have for every n in n, you have an intersection, okay? So this is for every n inside n, okay? You have the omega inside omega is uniform continuous on these interval from 0 to n, okay? And because uniform continuity can be formulated using these for all j and for all k, I can write it as the following. So let's keep the for all n, and I need for all j, so that's the intersection of for all j greater than or equal to 1. And then there exists a k means it has to be inside one of this k, so there exists a k, so it means the union. Okay, so now I have all the omega so that for every x and y, their distance, x minus y, is less than 1 over k. I have omega x minus omega y is less than 1 over j. So here x and y are going to be inside the interval 0 to n. Okay, so now you write it as one of these sets. Okay. So if you can give a good estimate of how large the measure of the set, and you can basically give a measure of their union, and then you take their intersection, okay? So that's kind of the idea if you follow Foland's textbook. And the estimation is going to be very, very technical. So here basically use the omega needs to follow these normal distribution because they're Brownian motions. So you have some estimate based on the normal distribution. I'm not going to give you all the detail. If you're interested, you can read Foland's textbook. But the idea is after you give the estimate, you estimate the mu of this measure, the mu of this set. Okay, so the mu of this everything, it turns out to be equals to 1. Okay, rather, you technically prove the mu of this complement is equal to 0. Okay, so that's basically shows that this measure mu is concentrated on those continuous functions. And the conclusion is Brownian motion exists. Okay, so B of t is going to be continuous almost everywhere. So you now have a definition of the Brownian motion.